Let me show you how to calculate the volume and the surface area of an n-ball. And by n-ball, I mean an n-dimensional ball. Now I'm going to assume that you already know these two results. So 2-ball, which is a disk, you know that the area is pi r squared and the circumference is 2 pi r. 3-ball, which is the usual ball, and I'm going to assume that you know that the volume is 4 over 3 pi r cubed and the surface area is 4 pi r squared. And we can easily use the methods in calculus to prove that these are true. And additionally, what I'm going to show you is how to get the formulas for the volume. Now, once you get the volume, then the surface area you get for free because you can see that there's a pattern. If you differentiate pi r squared, you get 2 pi r, because r squared differentiates to 2r. And if you differentiate r cubed, that's 3r squared, and 3 cancels, so you get 4 pi r squared. And you might think, oh, this is just probably a coincidence, but it's not. It's not a coincidence because there's a reason why that happens. So just think about the 3-ball, the usual ball that we have of radius r. Now, if you think about a radius r ball and you increase this ball of radius r just slightly, ever so slightly by dr, then the volume is going to increase by this much. And then if you think about how much the increment of the volume would be, you just take the surface area, S, and you multiply it by the thickness. If you multiply the surface area by the thickness, then you get the volume object, and that exactly describes the increasing portion of dV. So when this thickness is very, very small, infinitesimal, then you should get this result. And if you divide both sides by dr, then you can see that if you differentiate dV by dr, you end up with the surface area. Okay, this is somewhat akin to the fundamental theorem of calculus. And the fundamental theorem of calculus, what happens? If you have defined an area function from 0 to x, and here's f of x, then this area function s of x is going to increase its area ever so slightly if you increase this by dx. So if this portion is dx times the f of x gives you this extra area that s of x increases, so you end up with ds equals to f of x times dx, and that's how you know the fundamental theorem of calculus, which is that if you define the area function, the derivative of the area function is the function itself. In other words, the area function is the antiderivative of the function. That's basically the fundamental theorem of calculus. So this will be like a geometric version of the same thing happening, and the only difference is like here you're moving in one direction, here you're moving in all directions. Okay, so we are only going to do this calculation, and the other one would be for free. Okay. Okay, so before we move on, I want to show you how to calculate the integral of cosine to the nth power of theta, because if you do the calculation, the only challenging part is that integral. So once you know how to calculate that one, then other parts will be a lot easier. Okay, so we're going to do this calculation. First, break up the cosine nth power as cosine theta times cosine n minus 1 power. Integrate from 0 to pi over 2. And then we're going to take the integration by parts, which is if you have two things multiplied, integration by parts says you take one of them, find the antiderivative. You don't do anything to the other guy, but minus what you integrated, you don't do anything, doesn't change. But what you didn't do, that has to be differentiated. So that's the integration by parts formula, right? So I'm going to apply that to this here. Cosine has the antiderivative sine of theta, and I'm not doing anything to cosine n minus 1 theta. And then this is a definite integral, so you have to plug in the endpoints. Minus 0 to pi over 2. And since I've already integrated sine theta, we don't do anything, but whatever you didn't do anything to now has to be differentiated. That's the rule for integration by parts, right? So we have to differentiate cosine n minus 1 theta. But what is cosine n minus 1 theta? This is just a shorthand for cosine theta to the n minus 1 power, right? So you can use the chain rule. N minus 1 comes down. N minus 1 gives you n minus 2, and then you differentiate cosine theta to give you negative sine theta. Okay, so I'm going to plug this in here, which gives you n minus 1 cosine. Now I'm going to rewrite this as cosine n minus 2 theta times negative sine theta d theta. And then let's plug in pi over 2. Sine pi over 2 is 1, but cosine pi over 2 is 0. 0 times anything is 0. And then when you plug in 0, sine of 0 is 0, so again it's 0. So here, when you plug in these endpoints, you get 0 for both cases. For this integral, you have minus and minus, so this is plus 0 to pi over 2. Sine times sine is sine squared. And then you have n minus 1 cosine n minus 2 theta d theta. Since n minus 1 is a constant, let's move it outside the integral. So I'm going to put n minus 1 here. Integral from 0 to pi over 2. And then I'm going to rewrite sine squared as 1 minus cosine squared. Then if you multiply this out and split the integral into 2, this is what you're going to see. It's n minus 1 times the integral from 0 to pi over 2 of 1 times cosine to the n minus 2 is just cosine to the n minus 2 theta d theta minus n minus 1. And you have cosine squared times cosine n minus 2. These two exponents add up and you get cosine n theta d theta. Okay, so what are we seeing? We see that you started with trying to figure out what the integral of cosine n power theta is, and the answer contains the same thing. So it feels like we're going in circles. However, if you denote this as I sub n, I for integral, and the n for keeping track of this number, then we can rewrite this as I of n minus 2, and this one as I of n, and treat this as an algebraic equation. So let's see what we get here. We get that In, we just showed that In is same as n minus 1 times I sub n minus 2, and then minus n minus 1 times I sub n. Bring this over here so that you get 1 times In plus minus becomes plus if you go to the other side. You have n minus 1 In equals to n minus 1 In minus 2. And 1 plus 1 n minus 1 is simply just n times In. So that if you divide both sides by n, you get n minus 1 over n I sub n minus 2. Okay, great. So instead of being able to compute what this is, we just found out that there is this recursive relation. I sub n is n minus 1 over n I n minus 2. Okay, but let's not forget what in is. 0 to pi over 2 cosine n power theta. And let's just calculate I1 and let's calculate I0 and I1. So for example, I0, when n is 0, you get integral from 0 to pi over 2 of cosine to the 0th power, but anything to the 0th power is just 1, right? So you have just integral of 1 d theta, and 1 integrates to theta, and you plug in pi over 2 and 0, you end up with pi over 2. Okay, on the other hand, if you have I sub 1, you have 0 to pi over 2, integral of cosine to the first power of theta d theta, and the antiderivative of cosine theta is sine of theta, and then you have to plug in pi over 2 and 0. So you're going to get sine of pi over 2 minus sine of 0, and sine of 0 is 0, sine of pi over 2 is 1, so you get 1 minus 0, which is just 1. I forgot to say something when I was getting this recursive relation. Here, I'm really assuming that n is 2 or greater, or else when I did the integration by parts, when I plugged in pi over 2 and 0, we couldn't guarantee that one of them gives you 0. So things break down if n is 1 or 0. Okay, so at least this is what we have. We have I0 as pi over 2, I1 as 1. And then after this, we can just use this recursive relation. So for example, if I have I2, it's going to be, according to this formula, 2 minus 1 over 2, I of 2 minus 2, which is 0. And because I0 is pi over 2, you get 1 over 2 times pi over 2, which is pi over 4. Okay, let's do another one. I3. Well, 3 minus 1 over 3, I sub 1, and that's going to be 2/3 times I sub 1 is just 1, so it's 2 over 3. Okay, and you can kind of see that we can continue this forever and get I4, I5, and so on. But we also realize that there's a pattern which only holds for even and then odd separately. So we should really write down the formula for IN for even and odd separately. So let's do this. If n is even, then just like this, we're going to get something with a pi. Okay, so we get I sub n equal to n minus 1 over n times I sub n minus 2. But I can use this formula again for I sub n minus 2 by replacing this n by n minus 2. So in other words, I'm trying to say that, let me see, I sub n minus 2 is n minus 2 minus 1 over n minus 2, I sub n minus 4. That's how I'm trying to use this formula. And if I simplify that and apply it to n minus 2, I get n minus 1 over n times n minus 2 minus 1, which is n minus 3 over n minus 2. And then all the way down, and then you get n minus, eventually, see, if n is even, n minus 1 is odd, That's also odd. So you keep subtracting until you get to the smallest odd number, which is 1, right? And then once this reaches 1, you can't use this recursion anymore, so that's when it's going to stop. And because this denominator is always 1 more than the top, you're going to stop at 2. And then you're going to get well, see, this number is always 1 less than this one, so if you have 1, you get I of 0. And I0, we know it to be pi over 2, so it's going to be pi over 2. Now, let's choose a quite big number and see if there's any other way to write this. So let's say if n is 10. What does this formula say? That seems to say that you have to do 9 times 7 times 5 times 3 times 1 until you reach 1. And the bottom is always 1 more than the top. And then at the end you get pi over 2. Okay? Now, when you skip something by 1, there's a formula for that. I mean, the usual factorial is like if you have, say, 5 factorial, that means 5 times 4 times 3 times 2 times 1. But if you put double factorial, that means it's 5 times 3 times 1, so you go down by 2. So a way to write this as a shorthand is to write down 9 double factorial. And you could also do the same thing over here, but instead, when you have an even number, you don't use double factorial. Instead, what you use is you get to pull a 2 out. So if you rewrite 10 as 2 times 5, and 8 as 2 times 4, 6 as 2 times 3, and 2 times 2, and 2 times 1, then you see that you get 5, 4, 3, 2, 1. So you get 5 factorial, but you also get 2 to the 5th power. And then you get pi over 2. And that kind of gives you an idea of how to simplify this in general. The top one is going to give you a double factorial, whereas the bottom one will be n divided by 2 factorial, and you also get 2 to the power of n divided by 2. So let me rewrite the result above as equal to n minus 1 double factorial over 2 to the n over 2. So this is n over 2. And then times n over 2 factorial times pi over 2. Okay, now for n is odd, we can do the same thing, n minus 1 over n, I n minus 2. And this time you can do this again. You can do n minus 1 over n minus 3 over n minus 2, and keep going down. And because n is odd, n minus 1 is even, so if you keep going down, the smallest positive even number is 2, so you're going to reach 2, and the denominator you're going to reach 3 because it's always 1 more than the numerator. And then you get I sub 1 less than 2 is I sub 1. But what's I sub 1? I sub 1 is just 1, right? And this time, because the denominators are the odd numbers, the denominators will be represented using double factorial. And the numerator are all even numbers, so we can use the same trick that we've used before, which is 2 to the n minus 1 over 2 power times n minus 1 over 2 factorial. Times I1, but I1 is 1, so that's what you get. Okay, so that was the most challenging part. Once you are okay with this result, then the rest of the calculation will be a breeze. So hopefully if you've endured this much, then you're ready to figure out what the general formula is. So let me first write down the results. So In is equal to n minus 1 double factorial over 2 to the n over 2, n over 2 factorial pi over 2 for even, and then for odd, 2 to the n minus 1 over 2, and then n minus 1 over 2 factorial over n double factorial. Okay. All right, so now let's try to review how to get this result from the calculus. Well, the way we get this, of course, we can use polar coordinates to significantly simplify the calculation. We're not going to do that because I just want a generic formula. So think about 3D. Here's x, y, and z, and then you have a sphere. Something like this. And let's see, just like that. We're going to chop up this volume by taking slices perpendicular to the x-axis, so that all the cross sections will be two discs, so two-dimensional balls, two balls. Okay. So what I'm trying to say is that if I have an n ball and I take the x-axis, chop it, then all the cross sections will be n minus 1 balls, n minus 1 volume balls. So if we know that the formula is pi r squared for the area of the two disc, then we can say you integrate from x going from, well, let's make it simple and make it go from negative 1 to 1. So you can integrate from negative 1 to 1 of the pi r squared, and then you integrate dx. And then if you think about the radius of this cross section, well, since this ball has radius 1, hypotenuse will be 1, and radius will be r here, and this length from 0 is same as the x coordinate, right? So you can use the Pythagorean theorem and say, oh, okay, so r is really square root of 1 minus x squared. And this is true in any dimension. So it will always turn out that the radius of the cross-section ball will always be square root of 1 minus x squared. So you can rewrite this as pi times square root of 1 minus x squared, and then you take the square, you integrate, and you integrate from negative 1 to 1. And another way to save time is to just integrate from 0 to 1 to take only the right half portion. And then if you double this, then you get the same answer, right? So that's how we're going to do this. And the result of this calculation is, it's pretty straightforward. You're going to get this 4/3 pi r cubed. What about four-dimensional ball? Well, if you're doing four-dimensional ball, then although I can't draw four-dimensional ball, it's like this, whereas the cross sections, I'm drawing a disc, but it's really a three ball. So the volume of a four-dimensional ball would be, we plug this in, 4 over 3 pi r cubed, so that when you rewrite this as 4 over 3 pi of this thing to the cubed, you compute this, then that's going to give you the four-dimensional ball. And you keep going, okay? All right, at this point we should really define something. So we're going to define, as we've seen this IN being solved through recursive relation, we're going to do the same thing. We're trying to find some kind of a recursive relation between different dimensional balls. And to do that, I have to incorporate the same strategy here. We were successful because we had this subscript to keep track of the value of n, so that later when you had the recursive relation, we were able to use it over and over again. So what we're going to do is we're going to say that A2 is pi, which is this one here. And by A2, I really mean the volume of radius 1 ball. Okay, so it's a volume of the unit ball in dimension n. Okay, so the volume of the unit ball, when I say unit, that means unit ball, that means a radius 1 ball. So if I plug in 1 for r, you get pi. If I plug in 1 for r, you get 4/3 pi cubed. So I get A3 equal to 4 over 3 pi. And you might wonder then, what is A of 1? Well, if you have, in 2D, if you have a circle, and if we do the same idea, if we take cross sections, the cross sections are now straight lines. So see, in dimension 1, the unit ball is really, well, dimension 1 is just the number line, right? And unit ball means it's a collection of all points that's distance 1 or less away from 0. So it's this. And in dimension 1, the volume of dimension 1 is the length. So length of this is 2. So we have to say A1 is equal to 2. And then if you imagine taking this one and doing cross sections, then the cross sections give you zero-dimensional balls, and what's at the zero dimension is just a single point, right? And since we're adding these things, if I want the same kind of integral to make sense, then A0 should be defined as 1. Okay. Now you don't have to accept it. Later on you'll see that if the recursion is to be held for even for cases like this, we're forced to have this. So maybe if you're not fully convinced of this, let's put a question mark for this. Okay. So now what do we do? Well, if you know the volume of a unit ball, then the volume of radius r ball at dimension n would be, you just simply attach r to the power. So if I put r and then squared, because 2 is here, then pi r squared is the area, right? If I put r cubed for this 3, then this is the volume of 3 balls. So in general, the volume of radius r ball in dimension n is a sub n r to the n, where a n is really the formula that we're trying to figure out. Okay. If we know a n, then we know the volume of all n-dimensional balls, and then the surface area is simply you differentiate it, so it's not that bad, okay? Alright, so let's try to calculate this in dimension n. So how do we do this? Well, you have to say that a sub n is given by integrating from -1 to 1, but we're going to use that trick of doubling twice of 0 to 1, and we're going to do dx, where I'm putting v of r here because, sorry, this should be vn. It will be n minus 1, one-dimensional, but it will be a n ball with dimension 1 less, so it will be n minus 1. So I'm going to quote this formula with n minus 1, so it will be a n minus 1 r to the n minus 1. So you add these things as you increase x from 0 to 1, add them up, you get the n-dimensional ball, right? Now, we also know that r is square root of 1 minus x squared from that picture we had, so we're going to have 0 to 1 of a n minus 1 times square root of 1 minus x squared, and then you have n minus 1 power dx. Okay, now we learned in calculus that if you see a square root of 1 minus x squared, one of the ways to approach this is to use trigonometric substitution, right? So we're going to do trigonometric substitution with, let me write down the trigonometric substitution in case you forgot. We say x is equal to sine of theta, so that dx is going to be, if you differentiate sine, it's cosine, so it's like this. And also, if you have square root of 1 minus x squared, that's square root of 1 minus sine squared of x, square root of theta, sine squared of theta. And that's the same as square root of cosine squared of theta, which gives you cosine theta, okay? Now note that since x is always positive, this is positive and cosine is also positive if you use your theta to be from 0 to pi over 2. So see, when theta is 0, x is 0. When theta is pi over 2, x is 1. So here's the graph of sine of theta. So it's theta and x. So if you limit yourself to 0 to pi over 2, you see that when theta is 0, x is 0, and theta is pi over 2, x is 1. So as you know that this is the sine graph, and therefore you can rewrite the bounds as integral from 0 to pi over 2, a sub n minus 1, and then we just saw that this is going to be cosine, so it will be cosine n minus 1 theta times dx is cosine theta d theta, so that this is going to be 2 times 0 to pi over 2 of a n minus 1. This is cosine to the first power. If you add these two, you get cosine to the nth power theta d theta. And actually, this is where it gets painful, but we did the harder parts first, so we know that the answer to that is here, right? So we can rewrite this as 2 times a n minus 1. Pull this a n minus 1 out, and this integral, we know that it's I n, where it's this one, okay? All right, so we end up getting a quite complicated recursion formula. We can only relate a n with a n minus 1 by using this. But already we can get something interesting that we didn't know before. I mean, maybe you knew, but probably you're watching this video because you didn't know the volume formula for the four-dimensional bowl. So let's see how you can apply this to dimension 4. So if I want A4, then it's going to be twice of A3 times I sub 4, because I know that this is this, and then n is 4, so I put 4 here, 4 minus 1 is 3. And then it says here it's 4 over 3 pi, sorry, 2 times 4 over 3 pi, because that's A3. And what about I4? I4, well, this is the case when it's even, this is the case when it's odd, so for the even case is what we need. We plug in 4 here, so we get 3 double factorial on top. 4 divided by 2 is 2, so 2 squared. And then 4 divided by 2 is 2, so it's 2 factorial times pi over 2. And 2 cancels. This is just simply 3 times 1, so it's just 3, so these 2 cancel. 4 and 2 squared, that's going to cancel. You still have a 2 left out, and you get pi times pi, so you get 1/2 pi squared. So in other words, the formula for the volume of a 4-dimensional bowl is volume of the 4-dimensional bowl is going to be 1/2 pi squared r to the 4th power. And the surface area of the 4-dimensional bowl is you simply differentiate this. 4 comes down, it's going to be 2 pi squared r cubed. Okay, so that's what happens in dimension 4. Okay. Before we move on to the general formula, let's just do one more just to get a hang of it. Okay, so I5, what's that? I5 is 2 times A of 4 times I5. Well, we just calculated A4. A4 is 1/2 pi squared. And then I5 is this guy here. So it's 2 to the 5 minus 1 is 4. 4 over 2 is 2. 5 minus 1 is 4. 4 over 2 is 2. 2 factorial is what you get. And then 5 double factorial means 5 times 3 times 1. Okay? You can see that these two cancel. 2 factorial is 2. 2 squared times 2 is 8. And then 5 times 3 is 15. And you get pi squared again. So that tells us that volume formula for dimension 5 is 8 over 15 pi squared r to the 5th power. And then if you differentiate this, you get the surface area as 5 comes down, so it's 8 over 3 pi squared r to the 4th. Now, let me just say something here. Although this is the surface area of a 5 bowl, this is also known as the 4-dimensional sphere. Okay, so sphere is the surface of the 3 bowl. A 2 sphere is a surface of a 3 bowl, the usual bowl that we have, and the surface of a 3-dimensional bowl is 2-dimensional, right? So although I put a 5 here, this is really a 4-dimensional object. So this is the formula for the volume of a 4-dimensional sphere of radius r. Okay. Yeah. I'm saying this because if you try to compare the result that we had with something in the literature, you might find that the formula might be off by 1, and the reason is this. I'm writing this as S5, but the actual dimension of this object is 4. Okay, so in some formulas this will be something with the subscript 4 rather than 5. Okay. All right. So once you figure out the formula, let me rewrite it here. A sub n equals to 2 times an minus 1 I sub n. You can kind of see that, again, there's a pattern that emerges for even and odd separately. But there's another thing that you see. If you look at this calculation carefully, you see something strange. We had this 2 squared times 2 factorial here, right? That appears again. And it appears once in the denominator, then it appears in the numerator. So that if you apply this recursion relation twice, somehow these two things cancel and the end result becomes easier. So what I want to do is I want to show you a recursion not between an and an minus 1, but between an and an minus 2, because that'll be a lot simpler to write, and once we have that, then we can find the general formula, right? Okay, so let's try that. So let's start with n is even. Okay, if n is even, then we have an equals to 2 times an minus 1 times I sub n, which is, because it's even, we use this formula. So we have n minus 1 double factorial over 2 n over 2, n over 2 factorial pi over 2. Okay, but this means an minus 1 is 2 times an minus 2 I sub n minus 1, right? So I can rewrite this an minus 1 using that formula so that it's going to be, actually, let's do this. Let's cancel the 2's out so it's simpler. We're going to rewrite an minus 1 as 2 times an minus 2 I sub n minus 1, but look, n is even, so n minus 1 will be odd, so this time we're going to use this formula, okay? But this is the formula for n, so all the n I have to replace by n minus 2, n minus 1. So this is going to be 2 to the n minus 2 over 2, n minus 2 over 2 factorial over n minus 1 double factorial. So that's going to be my I of n minus 1, and this much is an minus 1. So I'm going to now copy this down here, and you see some cancellations now, right? So this is pi, and I see that these two cancel, and then let's see, this one has one less 2 than this one, okay? So in other words, when you divide the exponent and subtract, if you do this minus this, you get negative 1. And that extra 2 is going to cancel with this one. So all of these 2's are going to cancel. It's quite nice. And then finally, this is 1 less than this. So if you have something like k minus 1 factorial over k factorial, hopefully you've seen this before. This is like, it's like 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. So this is like 4 factorial over 5 factorial, just like this, right? And every one of these cancel and you just get this left out. So a whole lot of cancellations are going to happen, and you're just going to get n over 2, and then you have a pi. Okay. All right. So that's the much simpler recursive relation between an and an minus 2 when n is even. And once you see that this is what you get, you can keep applying this recursion again. So you can replace this by an minus 4, so that you're going to get 1 over n minus 2 over 2 pi times 1 over n over 2 pi. So this just carries over as before, but then I'm applying this same recursion with n replaced by n minus 2. So if I replace n by n minus 2, then this will be n minus 4, n minus 2 with pi there. So you get an identity for a n minus 2, and that tells you that a n minus 2 is this much. And you get one less than previous one. So you see that you get this one and then one less, and then you keep going, you get one less and one less until you reach 1. So eventually this is going to give you, because n is even, it's going to stop when you reach a0, and then you're going to get 1 over n over 2 factorial, and then pi is going to be multiplied n over 2 times. So that's what you're going to get if you apply this recursion over and over again. And I mean, you can either say, oh, okay, a0 is 1 if you were convinced at this result, or you can just say, well, I don't know what a0 is. It doesn't make any sense to say a zero-dimensional ball, but if I want this formula to be true for, say, n is 2, because n should be even, you can't put 3 here. For n is 2, I know that a2 should be pi, and plug in 2 here, it's pi, but then this is 1. The only way to make this true for n equals to 2 is when a0 is 1. So you can kind of force a0 to be 1, so that in general you have this formula, pi of n over 2 divided by n over 2 factorial. Okay. Okay, so that's just the even part. And that's a major result, so let me erase all this and write down our major result. an is pi to the n divided by 2 over n divided by 2 factorial, okay, for even case, n even. Okay, what if it's odd? If n is odd, then practically, okay, so since n is odd, we have to use this formula. So let's write that 2 to the n minus 1 over 2, n minus 1 over 2 factorial over n double factorial. But then I can replace this by this formula here, is 2 times a n minus 2, and I of n minus 1, well, because n is odd, n minus 1 is even, so I have to use this formula, except that since I have n minus 1 here, this formula should be used here with n replaced by n minus 1. So it's n minus 1 minus 1, so n minus 2 double factorial over 2 to the n minus 1 over 2, n minus 1 over 2 factorial times pi over 2. Well, I guess one of the 2's can cancel here. And then this, I shouldn't forget this one. This one still carries down here. It's 2 to the n minus 1 over 2, n minus 1 over 2 factorial over n double factorial. And it's nice because I see that these cancel, so you have something like 2 pi times n minus 2 double factorial over n double factorial a sub n minus 2. Now, we can simplify this as well. Just think of an example. We're looking for n odd, so let's say n is 5. What does that mean? That means it's like 3 double factorial, 5 double factorial. Now, this is like an example of this guy here. But double factorial drops down by 2, so it's 3 times 1, and then 5 times 5 minus 2 is 3, 3 minus 2 is 1, so that's what you get. And then again, you see something similar to n minus 1 factorial or n factorial that we just did a moment ago. Everything cancels except this guy here, so the same thing carries over, and this cancels, and you just get n as the denominator. So that's what you get as the recursive relation when n is odd, okay? Yeah, so if n is odd, then n minus 2 is odd again. That means I can use this recursion to itself. But in the next term, it's going to be 2 pi divided by n minus 2 times a n minus 4, right? Because if I take this recursion and replace n by n minus 2, this will be n minus 2 and this will be n minus 4, so this is going to be replaced by this one. And you keep going, and you see a pattern here. You have an odd number and you drop by 2, and eventually it's going to reach 1, right? If you start from any odd number and you start subtracting 2's, eventually it's going to reach 1, so it's n times n minus 2 until 1, so it will be n double factorial. And then the number of 2 pi's that you end up multiplying is going to be n minus 1 over 2. Yeah, this one you just have to spend some time thinking about why. It's not that hard to see, okay? And then because you keep subtracting, sorry. This has to reach 1, okay? So this really stops at 3, but even if you stop at 3, say if you have 7, 5, 3, and then even if you stop at 3, this is still the same as 7 double factorial, so I'm still writing that. And in that assumption, this should be the power. And then if you accept that a1 is 2, then you just plug in 2 and that's the answer. Or you can just write this as a formula that should be true for n3 and above. And just think about what would happen if you plug in 3. So if you have 3 here, well, 3 double factorial is 3. 3 minus 1 is 2, 2 over 2 is 1, so you get 2 pi. And a1 is like, well, the only way this gives you 4/3. I know that a3 is 4 pi over 3, that's what I need, right? So a1 has to be 2 in order for this to be true for 3. So you can kind of make an argument that this has to be 2. Right? Okay. So we have another nice formula for n odd, which is 2 pi to the n minus 1 over 2 divided by n double factorial. Right, double factorial, and then times 2 for odd. Okay. Now, it's a bit interesting, or you might say ugly, that you have different formulas for even n and odd n. So there's a way to rewrite this so that it's true for both n even and odd, and use something called the gamma function. Gamma is defined as integral from 0 to infinity of t to the x e to the t minus 1 dt. it's a bit weird, but you can apply integration by parts to show that this is the same as x times gamma of x minus 1. Actually, no. X minus 1 times gamma of x minus 1. And moreover, that gamma of 1 is equal to 1. And these two properties can be used to show the following. Another thing is gamma of 1/2 is equal to square root of pi, or pi to the 1/2 power. Okay, so these two properties can be used to prove the following, that if you have gamma of n plus 1, that gives you n factorial. So in other words, the gamma function allows you to rewrite the factorial as a continuous function. See, if somebody asks what is 2.5 factorial, you wouldn't know what to say. You would say, oh, that's nonsense. But using this formula, you can say, oh, that's a gamma of 3.5 is like, I'll put quotes here because that doesn't make sense, 2.5 factorial, right? So gamma is a way to allow factorials for even decimal numbers. And if you look at this and say that the volume of n-dimensional wall of R is this thing here, pi of n over 2 over, and let's use gamma function for it, gamma of n over 2 plus 1, right? And then r to the nth power. We know for sure that this holds true for even n because of this property, right? But what's interesting is that you can check using this fact and others to see that this indeed becomes this formula for n odd. So I don't know if there's a deeper reason why that's true. Unfortunately, my mathematical knowledge doesn't extend that far. All I see is that there's a way to express both even and odd in this case, so that the surface area of Sn will be, you simply differentiate this, so it's n times pi to the n over 2 over gamma n over 2 plus 1. Now, as I said, some people will be happy with this, but some might say, oh, no, we want to think of this as like an n minus 1 dimensional object. So another way to rewrite this is you can replace all the n by n plus 1 and rewrite it as n plus 1 times pi to the n plus 1 over 2 over gamma of n plus 3 over 2 r to the n as the volume of the n sphere. So volume of n sphere. Okay? And depending on the context, you might end up needing this formula. Okay, that's it.